A really important idea in probability is conditional probability. And we'll come on to later why it's so important, but let's start with some examples. As often the case with probabilities, it's often worth just putting in numbers to try and get some intuition about what's going on, and so you're not bamboozled by the equations. So let's take some data from the 2011 Irish census. So this is giving information about the number of families in the country. So that the number of families with no children is about 345,000. The number of families with one child is about 340,000. Number of families with two children, 286,000. With three children, about 144,000. More than three children, 75,000. And then the number of families with all children less than 15 years, well, that doesn't really apply when there's no children, obviously. There doesn't really make sense to even ask the question. If there's one child, 178,000 out of the 339,000 have the child less than 15 years. In families with two children, it's 92,000 out of the 285,000 of the both children less than 15 years, 30,000 when it's three children, and 8,000 when it's more than three. So suppose out of the families with one child, we pick a family at random. So that's our experiment, right? It's also worth, a good rule of thumb when dealing with data, to be clear in your own mind what the experiment is. Because if you remember back in their definition of probability, it depends on this experiment. And if you find it difficult to just state clearly what the experiment is, that's a warning sign, right? That there's something fishy going on, or something your setup's not like you think it is. So define clearly what the experiment is. A good tip for when dealing with probabilities and statistics generally. Okay, so here the experiment is, we imagine we have all the families in Ireland with one child. We pick one at random, each one being equally likely to pick, right? So it's an equally likely outcomes setup. And then we can ask, what's the probability that the child in that family is less than 15 years old? Well, we know how to do that, don't we? So we know that there's the possible outcomes. What's the sample space? It's all the families, so it's 339,000 elements in it. The event is that we have a family where the child is less than 15 years. There's 178,000 elements in that set, right? That's all the families. And so the probability is 178,000 over 339, which is about half. Now let's ask a slightly different question. Suppose now the event we're interested in, so it's the same question rather, but asked in a slightly different way. Suppose we've got F is the event that a family has one child, and E is the event that the child is less than 15 years. Then the probability, so this vertical bar is read as given, the probability that event E, that the child is less than 15 years, given F, which is the event that the family has one child, is exactly the probability we've just calculated. The probability the child is less than 15 years given the family that has one child. It's just what we've calculated, and so that's 0.52. We've just calculated it. And that's a conditional probability. We're no longer calculating the probability, for example, out of all families that all the children are less than 15 years. Here we're focusing just on the families with one child, so we're narrowing it down by conditioning. Oops. And so we can ask the same kind of questions in other settings. So let's do it with a dice. So suppose we roll two six-sided dice, one after another. The first dice comes up a 2. Suppose we know that the first one is a 2. And we're going to call that event F. Then we roll the second dice. What's the probability they sum to 4? So that's the probability they sum to 4 given the first dice was a 2. So that's a conditional probability. So how are we going to do that? So the sample space that we're interested in, it's not the full sample space, right? The event F, rather, that we're interested in is that the first dice comes up a 2, so that means the possible events are 2, 1, 2, 2, up to 2 to 6. There's 6 possibilities. Because we've restricted it to be situations where the first dice is a 2, we can exclude all the others. So that's like a restricted version of our sample space, right? Just the relevant part of the overall sample space. And then the event we're interested in is that they sum to 4, so that means it's a 2 and a 2. And so we can calculate our probabilities is just by counting as usual. So there's 1, 2, 3, 6 possibilities, 6 in F, only one we're interested in, so it's going to be 1 over 6. Let's try another example. Suppose the first dice came up a 6. And we ask again, what's the probability they sum to a 4? So the F is now that the first dice was 6, and the second one could then be anything from 1 to 6. So it says 36 now, there's just 6 possibilities there, right? And the event E that they sum to 4, well, the first dice was 6, so they can't sum to 4, so that's actually the empty set. There's no elements in it. And so the probability that they sum to 4, given the first dice was 6, is going to be 0 over 6, which is just 0. And so you can see that the conditioning can increase or decrease the probability of events, can make them more or less likely. So you shouldn't assume it just works one way. I'll let you look at that one, that's quite funny, XKCD cartoon. So we're getting towards the definition of it, right? We're trying to build up some intuition for the definition, the general definition of conditional probability. Now, the first thing to note is that it's a probability, right? So we're going to. So essentially, what we're doing, if you saw how we calculated it, what we did was we took our sample space S, and then we considered the subset of it that was consistent with F, with the event that we've assumed has happened. So like the first dice was a 2. So we can exclude all the events that aren't consistent with that because we're not interested in them anymore. We know they can't happen. And so what's that? If we write it in our set notation, that's S, the sample space intersection with F, which is just going to be equal to F, of course, because F is a subset of the sample space. But let's write it that way for now. And then the event, we can do the same thing, is restricted to the outcomes consistent with F. We're not interested in anything else. And so that's our event E intersection with F. And then we're going to, the size of those two sets, we can do our counting to calculate probability, or more generally, so this is our counting idea we just did, right? So we can count the number of outcomes in E consistent with F, the number of outcomes in the sample space consistent with F. So that's the number of elements in our events intersected with set F, the number of elements in our sample space intersected with F, and that's what we did in our calculations, right? That's our conditional probability. And when we plug that in, and do a bit of jiggery-pokery, turns out that's equal to this guy here, right? It's the probability of E intersection F over the probability of F. And the reason for building all this up is to try and motivate this guy here, so that when you see this guy, it doesn't look like weird or strange. It's a natural thing, right? Because that's actually the definition of conditional probability. So now we're at this point. So this is something to remember. Oops. Draw better. So the probability of E conditioned on F is the probability of the event E intersected with F. So that's the subset of events E that are consistent with F divided by the probability of F. And that's for that to make sense, you require the probability of f to be bigger than 0. If f is equal to 0, this doesn't make any sense. And in fact, conditioning on a probability which has an event which has probability 0 isn't defined. It doesn't make any sense. And one immediate consequence of that is if we multiply both sides by the probability of f, then we get the probability of E intersection f is the probability of E given f times the probability of f. And that's called the chain rule. That's an important one. We use that all the time. But once you remember the definition of conditional probability, the chain rule just follows, right? That's just a straight consequence of the definition of conditional probability. Now, sometimes this is called the fourth axiom, but but here I'm doing it as calling it a definition, right? It's kind of a half axiom, if you like. And it's quite important. So the conditional probability is really important for all our machine learning ideas. In machine learning, we're interested in making predictions. If you remember back to week 1, if we're in the shopping and we have some items in our basket and we want to make a prediction, for example, about what we might buy next, then F is what we have in the basket, right? It's the contents of our basket, and E is the probability of what we're interested in next, and so these conditional probabilities where we have some existing observations and want to make a prediction, this is exactly the quantity you want to work with for making predictions. So it's really a central quantity. It's really, really important. Let's try some other examples. Suppose we flip a coin twice. Suppose the first flip is heads. What's the probability of 2 heads? So our sample space, we know already, is four elements. The event that the first flip is a head is the restriction of F, right? It's the subset of this set of possible outcomes where the first head is F. First coin is a head. So it could be a head and then a head or a head and a tail. So there's 2 elements in that. The event we're interested in is the probability of 2 heads. And so the probability of E given F is going to be the size of event E, which is just 1, divided by the number of elements in F, which is 2, so it's a half. Or we could go back to our definition and look at E intersection F, which is just, and the probability of E intersection F. So that means there's the probability of E is going, E intersection F is just E here, right? It's just 2 heads. So there's 1 element in that, and the probability of that, and there's out of 4 possible outcomes, so that's 1 over 4. The probability of F has 2 elements out of the 4 possible ones, so it's 2 over 4. The 2 4s cancel, right, on top and bottom, and we're left with a half. So the definition gives, you can get it directly from the definition, or we can get it directly by looking at the sizes of the sets E and F. It's the same thing. And I'll leave you to check this, but the conditional probability, it really is a probability. What do we mean by probability? Right now, we're not just saying words now, right? We can be crisp, we can be clear about what we mean. We mean it's a quantity that satisfies our 3 axioms. And so we can go check them. There's axiom 1, axiom 2, and axiom 3. I'll let you check it yourself offline. But do check it, don't just take my word for it, because you don't need to. You can go check it, right? You can see the ideas here are very straightforward. It's just like one-liners, just combining sets and stuff. It's all very straightforward. And you can confirm that it really is a probability. You don't have to take my word for it.